Yet again, another pleasure to be hosting the webinar series from Pharmacometrics Uganda, Pharmacometrics Africa Uganda chapter. Today we have Professor Haworth from the University of Southern California Mann School of Pharmacy and Pharmaceutical Sciences. Professor Haworth is an associate professor and the vice chair of the Department of Pharmacology and Pharmaceutical Sciences. He has from the postdoctoral studies from the University of Oxford. Over the last 3 decades, he has been teaching medicinal chemistry and biopharmaceutics. His research lies at the interface of chemistry, biochemistry, and computational research in pharmacodynamics and pharmacokinetics, with a broad experience using techniques like PBPK. I want to first acknowledge that it is very early where he is, and also use the opportunity to really appreciate his experience. Professor Ian, I'll hand over the mic to you to start the presentation. But in the meantime, all the attendees, please, if you have any question, have any comments, type in the Q&A section of your Zoom link as the presentation goes on. We will have approximately 40 minutes of presentation and 20 minutes for questions and answers. Thank you very much. I'll hand over to Professor Haworth.
Great. Well, thank you, Francis, and thank you everybody for the invitation to talk in this series. I thought I'd start off with this picture. This is Santa Monica Bay in Southern California. We're looking at actually over here. We're looking at Malibu, which is actually not where university professors live. I'm afraid that's reserved for other people. But I'm speaking to you just off of the corner on the right here. So I'm really lucky to live in Santa Monica. It's about 20 miles. West of Los Angeles and 20 miles west of the USC campus. Beautiful place to live, and I recommend that you visit if you have the opportunity. So that's where I'm speaking from you. It is a little bit early, so I apologize if I'm a bit slow, but I'll do my best. So I gave this title, Understanding ADME Using Physiologically Based Pharmacokinetic Modeling, to have sort of 2 meanings. One is the teaching perspective. PBPK modeling is becoming more and more common. I see the huge interest from students in master's, PhD, and actually in professional pharmacy programs in this method. And so I have taught this kind of methodology for a few years now. I really thought about how the best way is to teach it, and that's not so easy, as I'll talk about a little bit. And then there's the understanding there, which really means learning at the student level. And then the second meaning of understanding is really to look at ADME of, as I will show you, common drugs, really common drugs, and understand more about them, because it turns out, I think that there's a lot to learn still about the behavior of drugs that everybody really thinks are fully understood, but it turns out that they're really not. So that's what we're going to do. And I thought I'd start with a little bit of a different thing, though, just to tell you a little bit about myself and what my lab does overall. I am actually a chemist, and my training is in physical organic chemistry, as well as computation. So my lab has been based actually for many years more in this red circle of modeling, informatics, and writing algorithms. We still write a lot of algorithms in this area, and this is really looking at molecular interactions. Along with everybody else, I started to take on AI issues more recently. I'll just give a little plug for a program called NIME here. This is a not my software, it's free software. It's beautiful platform for doing machine learning, very intuitive, and I really encourage people to have a look at that. I'm not going to talk about that today. And then the other area of my lab now, very important area, is PBPK modeling, primarily using GastroPlus. And this is, of course, what I'm going to talk about today. I really see these red, blue, and green circles as interconnected. And in fact, one of the things we're trying to do is bring a more molecular view of PBPK. And what that really means is bringing molecular structure into PBPK more in a three-dimensional sense. I really don't have time to talk about that today, but this is, I think, a connection that's important to start to appreciate conformational issues that can affect pharmacokinetics. And then, of course, I'm in a university, and so obviously I'm very interested in education as well, and that includes bringing all of these areas of computation into a pharmacy curriculum, into pharmacy and pharmacology curriculum, and so I'll talk a little bit about the challenges of doing that. And we were just talking before the webinar about the idea that PBPK modeling is a field that you have to move into from other fields. I'm moving into it from chemistry. Other people can move into it from physiology. Very different backgrounds, still doing the same techniques. And so I really encourage people, regardless of your background, you have something to bring to this field. And the perspectives are very different from if you have different backgrounds. And so look at my approach to PBPK modeling as the approach of a chemist, trying to then appreciate the physiology. And I think you'll see that, I hope, in the next half an hour or so. Okay. Let's just talk a little bit about ADME. This is my big overview slide. I'm sure most of you are well aware of many of these issues, but let's just briefly establish the context of this talk. And so, as you all know, drug given in a tablet, it has to dissolve. The rate at which that happens, typically in the stomach, is important, and it's going to depend on largely the physicochemical properties of the drug and also the formulation. Once it has dissolved, most drugs, not all, but most drugs will ionize. And so there's going to be an equilibrium set up between the neutral species and the ionic species broadly. And then that neutral species, if we're thinking of passive diffusion, is going to partition into what for the moment we'll consider to be a gut wall lipid barrier. And that's largely going to occur in the small intestine at roughly pH 6. And the drug is going to be driven through the gut wall through a series of equilibria, with these equilibria shifting from ionic to neutral, partitioning from aqueous to lipid, and then out into the portal vein. And the total amount of drug that reaches the portal vein is then the fraction dose permeated. So all of that's happening, but of course the other thing that's important here is that only has a limited amount of time to happen. It's always difficult to know exactly what that time is, but let's say the order of about 3 hours, at least in the stomach, duodenum and jejunum. And so this has all got to happen reasonably quickly. So that's the absorption piece, at least part of it. If we go over to the right here, here we've now got the small intestine. So everything on the left is happening here in the small intestine. But we've also got other mechanisms of absorption. The most important other mechanism for small molecules, at least, being transporters. So there are transporters that can carry drugs from the small intestine into now not a lipid barrier, but a cellular barrier into the epithelial cells that line the intestine. So if we're concerned about including those transporters in a model, we better know something about the kinetics of that transport. We better understand Vmax and Km, the Michaelis-Menten parameters. There are also transporters, efflux transporters, that push drugs back. And so that can be an issue. I won't talk about that today, but that can be an issue for some drugs. Let's assume the drug successfully negotiates this barrier. It's now going to emerge into the portal vein, and it's going to start distributing to tissue. So that's the D in ADME, and the first organ that it encounters will be the liver in the first pass. And what may happen is that the drug will, in some way, either through a transporter or just through passive diffusion, move into hepatocytes. And in those hepatocytes, it's going to encounter, amongst other things, CYP enzymes, the main metabolic route for most drugs. So that's the M in ADME, and that is going to lead to chemical change of the drug, metabolism, formation of metabolites that may be eliminated, and that's the E in ADME, may be eliminated through the bile or the feces, or may come back into the systemic circulation and be eliminated in the kidney. And the drug may also just not, in fact, enter the hepatocyte, but ultimately be eliminated unchanged through the urine. So there are lots of different mechanisms here that we could explore in a lot of detail. But again, if we're thinking about this in terms of a model, in terms of a physiologically based model, we've really got to understand enzyme kinetics. So the kinetics of the CYP enzyme, we need to understand the expression levels of the CYP enzyme. And then if we get into more complex models, if we're looking at drug-drug interactions, then we've also got to understand enzyme inhibition. So that may be one mechanism of a drug-drug interaction. So lots of detail there needed in order to start to build models. If we look in the kidney, and we're thinking here is the kidney largely as an organ that's going to eliminate either the metabolites or the original unchanged drug, we must understand mechanisms like glomerular filtration, because that's going to be an important mechanism of elimination for some drugs. We need to also understand active secretion, meaning through a transporter, because there are many protein transporters in the kidney that will also eliminate drugs. And as I'll talk about a little bit later, we also need to understand reabsorption. So some molecules will be on their way to being eliminated through the urine, either by filtration or active secretion, but then they can be reabsorbed back into the systemic circulation, and that can have a big effect, of course, on the pharmacokinetics. And so this is something I'll talk about a little bit. So in a nutshell, these issues on the right-hand side, plus these physicochemical issues on the left-hand side, are really what goes into a PBPK model as parameters. So we really need numbers for all of these data. And that's, of course, not so easy. Some of them can be predicted. Some of them can be determined experimentally. But they're all needed. And then the other thing that's needed is more anatomical and physiological issues, such as the size of the liver, the size of the kidney, the rate of blood flow, and moreover, how those things change in different genders, different ages, in disease states, all sorts of physiological issues to deal with. So if you put all of that together, you have your PBPK model. So let me spend just a little bit of time here talking about teaching, because I think from what I've just said, it's clear that you need a lot of understanding of a lot of different things to appreciate PBPK modeling. You on the one hand need to understand the physicochemical properties, the physical chemistry of what happens to a drug at the molecular level. On the other hand, you need to understand enzyme kinetics. You need to understand transporter kinetics. And that's really quite a different field. And then you've got to be able to put all of that together in a, not in a test tube, but in the physiological environment of the human body, and understand basic physiology and pathophysiology. And that's not so easy. And then the other problem is that in doing that, you've actually got to be able to use software as well. And software, be it GastroPlus or other softwares for PBPK modeling like PKSim and SimCit, are complex to use. And so this is really a challenge. It's not so easy to understand the science. On the other hand, understanding of that science might be increased if you can use software well. So this is the challenge. How do you teach these scientific principles to people who are aware of them, but certainly not experts in them yet? And how do you also teach software operation in parallel? So we thought about this, and I'll mention Noam here a number of times, Noam Morningstar-Cui, who is now works at Simulations Plus, but worked with in my lab for several years. Noam and I put together this idea of a template for teaching. There's a few references. You can watch an entire webinar on this from a couple of years ago. And we also published it recently. And basic idea here is that there are scientific principles that you need to learn. And then if you understand those principles, you should be able to start to make some kind of predictions of what might happen in the software. But this is really limited. It's just one principle, use the software. So this is the use. And of course, that is a learning process in itself. And then once you start to be able to use the software, you can do simulations, you can get results, and then you kind of go back to this scientific principle idea to validate your results. Do your results make sense based on your understanding of the principles? So this is to validate, and you keep going in this circle of these three outer circles here. And really, once you start doing this more fully, and you start mixing up these principles, mixing up different ways of using the software, doing different applications, you're doing PBPK modeling. Sounds easy enough, not so easy, of course, in practice. Quick example, this is the same template, but now something specific. We're thinking about physical-chemical properties of midazolam. So what would we understand about midazolam? Well, it's a weak base, let's say, and the pK, it turns out, is 4.5. So let's understand that. Let's then use the software to generate a pH solubility curve. And what does it look like? It's low solubility at high pH. After you get ionization at lower pH, you see the solubility increase. So you're validating at this point that result. But you can go a little bit further. In fact, a lot further. You can do a simulation if you know how to do it in the software. And what we're seeing here is over time, midazolam in solution. So in solution meaning in the gut, in solution. And the blue curve is the amount absorbed. And we can see that there's a little bit of a dropout of solution here because as we're doing this simulation, the pH is changing. But basically, the midazolam is all dissolved. This is 3 milligrams. The whole mass is dissolved, and all more or less all of it absorbed after an hour. So we can understand that in terms of physicochemical properties, but then can we link it? So this is really the application now to actual data. And so these are data from this paper here, Brighthaupt, just a random selection. But this is midazolam 3 milligrams oral. Let's just focus on the immediate release tablet, which is the triangles. And you see time after administration, plasma concentration, that the peak, the Cmax, is reached after about an hour. So this is somewhat consistent with what you'd expect here, that this drug is dissolving quickly, it's absorbing pretty well, short Tmax, rapid absorption. So you can go from really quite basic physicochemical principles through the behavior of the drug in the gut to actually accounting for, in a broad sense at least, the pH, the plasma concentration versus time profile. So that's the kind of thing that we want to do in a teaching context. And really, that is also what we do in a research context. And it's really not all that different. But of course, in a research context, we're building much more complex models, and these physicochemical processes are just the beginning, really, of the model. So here now is a depiction of the PBPK modeling process, and again, lots of detail here that I won't go through, but just to make the point that broadly there are parameters that represent the molecular behavior of the drug, the physical chemical properties. There are also parameters that represent the formulation, and this, of course, is extremely important for modifying the behavior of the drug in vivo in the gut. And here we're talking about oral absorption. Then there are parameters for enzymes and transporters that the drug is going to meet along its journey. And then there's the broad physiology that this is all happening within. And then intrinsic and extrinsic factors, which I think are not really put directly into the model, but are used to modify other parameters. So pharmacogenetics, for example, may affect expression levels of certain proteins. Disease state may do the same. Food may influence solubility, for example. So these, and you could think of many other ones that could modify these basic parameters. Once we've got all of that, we go to the PBPK model. I'm really going to skip over the details here, but basically in Gastro Plus, you have the so-called ACAT model, which deals with absorption, and it allows you to model the progress of the drug as it moves through the stomach and the small intestine. The drug then is absorbed eventually into the portal vein and eventually into the liver. And then the so-called pair model is the physiology model. And this has all these tissues as different compartments. They have defined sizes. They have blood flow in and out. And those parameters change with age, for example. And all of that is in the hands of the user. And if you run your simulation, you then have, the most important thing is to validate your model. So you'll see in the next 15 minutes quite a lot of these kind of curves. So what we're looking at here is the simulated curve in blue and the observed data within the open symbols. And so this is, again, a simulation time versus concentration in the plasma. And so this is in actuality the time after administration of a drug. And of course, the goal is that your simulated curve, your line here, matches with the observed data, which of course in this case it does. But that is only really achieved through manipulation of all of these parameters. How can we measure that? We can measure it by showing that Cmax is consistent between the observed and simulated data, that the area under the curve is consistent. If we're looking at a drug interaction, that the elevation or reduction of the victim drug is correct. But I also put in a number of other things here, because one of the things that I want to just emphasize in the next few minutes is that fitting the plasma profile, the plasma concentration versus time profile, that is absolutely important and is really the starting point. But it's also very important to try to use other observed data. One of the most obvious ones is urine accumulation. So can you show that your model is predicting the correct elimination kinetics of pharmacokinetics of the drug? There's other ones though. If you have multiple enzymes involved or just one enzyme, how much of your drug is being metabolized? Can you reproduce that? So this will be percent metabolized out of the total dose, or if you have multiple enzymes, the ratio of the metabolism by the different enzymes, and there are other things as well. So the message here is, yes, fit the plasma concentration time curve, but be careful because you can fit that curve very well, and you may find out, as I'll show you for one example, that your model is really not correct, even though your curve fits well. Once you've done all that, you can apply the model. And that's, of course, the real goal here. Create a model in one population, apply it to different populations, to different formulations, and to derive mechanistic understanding. And I think the third one here is the one I'm really going to talk about for the next few minutes, mechanistic understanding. So before we go there, let me just say one thing about depiction of the construction of a model. And I will now show you some names here just to make sure I give full credit. So Sofia Provenzano is a student in my lab, and she makes great figures, and so she thought about this problem of how do you show the evolution of a model. And this is really important, because when you start modeling, you generate your baseline model, which is essentially just the default parameters in GastroPlus in this case. It's usually not very good, and that's the truth. And you know, we're not in the prediction game here yet. This is a basic model. This is the simulation. Again, the observed data are here in the open symbols, and that's typical. You know, it doesn't work at that point because we have to adjust parameters, and this is very much the case. So what do we do here without getting into any detail? We adjust the permeability. And so what's been done here is the old curve, the baseline curve, is now shown in the dotted line. The new curve is the solid line after the adjustment of this permeability, and the experimental data, observed data, is still the same. And so you can start to see how this changes. And then we change Vmax. I think this is fluvoxamine, so we're changing the CYP2D6 kinetics, and we're getting closer. And then eventually we optimize what are known as the absorption scale factors. This is modifying the absorption parameters for fluvoxamine. And finally, we get, after a further change in Vmax, we get our curve to fit. But the point being here that the curve from the previous step is shown as a dotted line. So you can see very nicely how the model is changing. So this is the depiction. Of course, you have to have a justification for each of those changes that I'm not going to get into for fluvoxamine, but this approach I think is quite a good one, and it may be that this is somewhere else in the literature, but I don't really see this done sufficiently, I think, in terms of showing how models are built and really being able to appreciate the model building process. This is important. It's not just the final model that matters. It's how you got there and what's the rationale for each change that you made. That's really mechanistically, that's where I think the learning occurs. So now another example for a very common drug, metformin. I don't have a lot of time to talk about this, but just to show you the potential of modeling to understand mechanism. Metformin is, as you can see, a very small hydrophilic, and it's actually positively charged at physiological pH. And, and so this looks like a prime candidate for paracellular absorption between the cells. And this figure here is the original figure from this really important paper on metformin from Thacker's laboratory, Proctor et al., a beautiful paper that really lays out the proposed absorption mechanism of metformin. The problem is, as they discuss at length in the paper, is that you would expect the metformin to be paracellular, and it turns out that it is. But when you look at a plasma concentration versus time profile of metformin, fasted conditions, it's broad, fed conditions, it's even broader. This is not really what you expect for paracellular absorption. You might expect it to be much more rapid, but it's not. So what's going on? So Proctor et al. Argue that what is actually happening is that the metformin is not all immediately transported paracellularly or absorbed paracellularly, but in fact, a lot of it moves into the epithelial cells through a transporter, is sequestered in those cells for a while, then comes back out through a transporter and moves through the small intestine and eventually is taken up paracellularly. But this accounts for this broad curve. So the question is, can that be modeled? Pretty complicated to model all of that. Auguste Cancum, also a student in my lab, but now working with Simulations Plus, did all of this. Again, I'm not going to get into a lot of detail here, but just to make the point, this is first, so how do you start? How do you approach this problem? The way we did it, and I think that the appropriate way to do it in general, is look for IV data to start with. In this case, there's plenty of data. We use 3 studies here, and we were able to simulate the IV data after altering some parameters, including transporter kinetics for, in the green here, these are kidney transporters, and the blue are liver transporters. So we can get the plasma concentration time curves quite well. As I already mentioned, it's important to also limit your model in other ways. So in 2 of these studies, they actually measured urine accumulation, and we were able to, not perfectly, but pretty well capture those data as well. So that means we're feeling good about our IV model. So let's go to oral. We now really had to work on this, and this does not in any way give credit to us is hard work on this, but basically we now have to put parameters into the gut. It's complex because we've got transporters moving the metformin into epithelial cells, back out of epithelial cells into the intestine, and also on the basolateral side of the gut wall, moving the metformin into the blood. And so all these data capture that, and we've also got, of course, the paracellular route going on. And again, we are looking at multiple studies over different doses, and we can capture those observed data pretty well. And eventually, the final test here is to look at the percent of metformin moving paracellularly and the percent moving transcellularly via transporters. And this is the observations in previous work is it should be maybe about 90% paracellular, and we're not completely there, but we are pretty close. And so this is the final check on the model, and this again is important that you have all these different observed data to show that your model is correct. So just last few minutes here. This is a drug-drug interaction module in GastroPlus, and I don't have time to go through all the details here, but the important thing here is that you need PBPK models for both of your drugs, for your victim drug and your perpetrator drug. And this module is generally run within the PBPK physiology of the victim drug. So that's loaded in. And then you bring in the PBPK model of the perpetrator drug, and then you run the simulation first for the victim drug on its own, and then for the victim drug in the presence of the pharmacokinetics of the perpetrator drug. So here's a quick example. This is tizanidine and ciprofloxacin. This is an interaction that's really confused people for many years because, as I'll show you on the next slide, there really are some questions about the concentration issues here. No time to go through this, but Sophia built tizanidine and ciprofloxacin PBPK models. This is just showing some of those, some of that process. So we have the two models, and so let's look at what happened here. So the basic background here is that ciprofloxacin is a CYP1A2 inhibitor, IC50 220 micromolar. So that's very high IC50. You need a high concentration of ciprofloxacin to inhibit CYP1A2. Tizanidine is metabolized by CYP1A2, so qualitatively you can see that ciprofloxacin could block tizanidine metabolism, and that does happen. Ciprofloxacin elevates tizanidine, and this is contraindicated because this causes a hypertensive effect, very serious hypertensive effect. But the problem is that when you look at models of ciprofloxacin, you look at concentrations, plasma concentrations, and you build your PBPK model, you really cannot get evidence that there's much of an effect. 45 micromolar, so what we're showing here is the liver concentration of ciprofloxacin. It only reaches 45 micromolar. So it's well below this IC50. I should add here that there's a lot of detail here, but this study that we're simulating here is multiple dosing of ciprofloxacin. What we really don't see the drug interaction to the extent that we expect. We can create it by reducing the IC50, but that's not really meaningful. because it's not correct. What we see, though, and there's good experimental evidence for this, is that actually over time, ciprofloxacin does accumulate in the liver. And when you add that to the model, you see this is the accumulation here, and you then get the correct curve for tizanidine in the presence of ciprofloxacin. So a lot of detail there, but the basic point here is that by building the model correctly and by including this liver accumulation, you can get the drug interaction. And mechanistically, that's certainly telling us something about ciprofloxacin. Last slide here, last example, just again, a kind of cautionary word. Another student in my lab, Aditya Savannah, who's done some great work, and he, amongst other things, built a caffeine model. So here's caffeine, and you think, well, how can that be complicated? And it didn't seem like it was. His model's beautiful. It took him a very short amount of time to do this. Plasma concentration time curve in dark blue here is perfect. So we were happy until we looked at the urine accumulation in the model. And in fact, what we found is with this perfect curve, our caffeine elimination in urine was totally wrong. In fact, everything was being essentially eliminated and changed. That's not right. In fact, it's exactly the opposite. Caffeine is actually metabolized almost completely. And so that led to much more work, eventually understanding that we must include significant caffeine reabsorption in the kidney. And once we've done that, we can still reproduce the plasma concentration time curve. But now we are also getting the full 90-something% metabolism. So this now is correct. But it would have been very easy for us to just sit on this plasma curve and say we're good. But we would not have been, this would have been really quite wrong. So again, this idea that you must use additional data. So just to sum up here, be systematic. That's really important. Depict your changes clearly as you build the model. Got to justify every change physical-chemically, physiologically, using whatever data you can find. Got to use, as I've just mentioned, more than plasma concentrations, if they're available, of course. Urine levels, metabolism, different transporter routes, amounts transported by different routes. Haven't really got into this too much, but be critical of the physiological parameters that are being used. They may not always be correct. The transit time can change quite significantly for certain drugs, for example. Where you can use observed data, experimental data for enzyme and transporter kinetics, but they can be changed. Hopefully not too much. I think that's a question in the field. How much should those really be changed in a model? What can be justified? Once you've done a good job building your model, then you should believe them, as long as you've done the models well. And then if something's not working, and unless you make a certain change and it's against an orthodox view, it may well be that the model is correct. So, number 6 is really believe your models once you build them, but build them very, very carefully. This is rather a specific, but I think this issue of liver accumulation is a little more important, perhaps, than people realize. From my perspective, I still think about this problem as a chemist, and I think that's very important. And then finally, just to comment on how we approach modeling. We really do work as a team in the lab, and most of the things that we've solved have been solved in group meetings. We talk about the model, we have someone build the model, we critique what they did, often very, very severely, quite honestly, and we tell them, no, that's not right, you've got to do that, and that's okay, that's a good dynamic. And I think that's actually a useful thing to remember. Build the model on your own, perhaps, but then present it and allow people to criticize it, and that's how you make progress. So just a few acknowledgements. I mentioned Sophia and Aditya and Oz and Noam already. I do want to mention Palak Agarwal, Sanskriti Sharma, and Lishuang Wong, whose work I didn't really focus on today, but they've all contributed in this team approach to the same data in the lab. I really want to thank Simulations Plus, as ever, for providing a license to Gastro Plus. This is remarkably generous, and this is, for those of you who are not aware of this program, this is the Simulations Plus University Plus program, and you can read about it and you can get a license for free at this URL. And then if anybody has any questions that come up after the seminar, or if you're watching the recording of this, please send me email at ihowarth@usc.edu. So thank you very much for listening, everybody. I hope I've illuminated a few issues in PBPK modeling. Thank you.
Thank you very much, Professor Haworth. I think this was really insightful. We have about 11 minutes for the Q&A session. There are already 2 questions in the Q&A tab of Zoom. I'll quickly read it, the questions, just in case you're not able to see. Do you see the Q&A tab?
I can now. I'm just looking, but let me see. Actually, no, I can see the chat. Are they in the chat?
No. So there is another tab, Q&A somewhere. I could also read the questions for
yeah,
you.
just read them. That'd be good. Yeah.
So the first one is from an anonymous attendee. I don't know who this is exactly, but the question is, given the challenges of replicating models from published papers, how can we ensure that our methodologies are robust and transparent? That's the first question.
Yeah, that is a great question. And I'll just preface that by saying I think that question is something that this entire field really need to think about carefully, and particularly those of us who are lucky enough to be doing this in an academic center. You know, in industry, it can be a little bit different. There are deadlines, there are other reasons for building models quickly. If you're doing this work academically, that question should be the foremost in your mind. So yeah, how can we do it? So I think, first of all, by trying to develop very limited, restricted, and rigorous approaches. So in other words, by every time you build a model, doing it in certain steps, and making moves in the modeling that are consistent. That's not so easy because, of course, each drug has its own problems. But I think it can be done to some extent. So that's one thing that I've been thinking about. The second one is, I think, documentation, trying to show the effects of a parameter change in the model. Now, again, often there are many changes being made, so it's not so easy, but at least when it comes to publication of a model, showing the most important steps. At least everybody recognizes that there's a lot of back and forth, but at least the most important steps. What worked? What made the change? What was the rationale for that change? And using, in a practical sense, in a manuscript, using the supplementary information to show that. It's a lot of detail, but it really helps other people in the field understand where your model came from. That's the transparency part. And then the third thing is just trying to use as much data as possible. And and even accepting perhaps that your model isn't going to be perfect for all the data, but using as much as possible to limit the model where you can.
Thank you.
Really good question.
I think that's actually a subject that Joshua and Davis are trying to pull out some literature on reporting of parameters in PBPK models. So I think probably they would seek some guidance from experts in the field. So the next question is from Sandeep, and the question is: physical chemical properties of monoclonal antibodies are important to modeling. It's stated more as a statement rather than a question, but I think he's asking whether physical chemical properties of monoclonal antibodies are important to modeling.
Yeah, so I would. So the PBPK modeling of monoclonal antibodies is, of course, quite different to modeling of small molecules. And at least in the sense that the properties of the molecule are going to be different. Of course, first of all, it's unlikely to be oral, so that isn't going to matter. It's much more likely to be a different route of administration. Also, the properties that cause the distribution of the antibody are going to be very different to those that control distribution and elimination of small molecules. So I have very little experience of that kind of modeling. I think the basic premise of the modeling is the same, that you're trying to consider the distribution of the antibody into different tissues and and how quickly it's eliminated, but the parameters that you put in are going to be really different. And I didn't show you any of this work, but we have been trying to model semaglutide, which of course is not an antibody, but at least it's a much larger peptide, and there, even there, you start to see that you have to really think a little bit differently in terms of oral absorption, at least in that case of semaglutide. The properties that you use are a little bit different, and the way that you go about the model is different. So yeah, I think this is a great area, not an area I'm certainly have any expertise in, but I see increasing number of papers in that area, and I think the parameters are different, but the principles are the same. It's the exact same process of reproducing experimental data and then having confidence that your model can predict.
Thank you. Ida has a question. I'll allow, I think she can unmute and pose the question. Ida.
Thank you so much for such an insightful presentation. Francis, can you confirm if you can hear me?
I can, yes.
Loud and
Okay, good. So 3 questions real quickly. You alluded to one of them. I come from a background of poor PK modeling, and in there we have very clear guidance on how to make changes. You know, what sort of changes do you make first? So for the question to you is, in PBPK modeling, is there some sort of criteria? You know, do you change the parameters of the drug first vis-a-vis the parameters of you know, how do you do it in a stepwise manner? That is one.
Understood. Yeah. Shall I answer that first, or do you want to ask all 3?
Let me ask all 3 really quickly.
Okay.
The second is, thank you so much for showing that you can use urine data to sort of also help in the validation process. Further to that question, what other sort of data can we use if it's not just plasma data? And lastly, maybe this is a whole talk for another day. Could you please throw more light on if you had data available, for example, from animals who have maybe had the same drug, but it's data in an animal? Do you essentially need to change the PBPK model to be one of an animal? to be able to sort of use that, or can you find a way to validate a model in humans maybe and link it to data that you observe in animals? Thank you.
Yeah, okay.
Thank you,
So,
Ida. Prof. Haworth, we have about 2 minutes. I don't know how you're going to manage.
Okay, I better be quick. Right.
Yeah.
No, great questions again. Thank you. And so the methodology, we've really tried to do this in the lab. In fact, we have a lab spreadsheet that we kind of joke about, that you cannot deviate from the spreadsheet in terms of changing parameters. And so, for example, if you're starting with an IV model, we would really look at three things. We'd look at log P, we'd look at protein binding, and we'd look at red blood cell plasma ratios, and we would change those systematically depending on experimental data. And so, for example, if we're over predicting, let's say our clearance, we might alter the protein binding, because that may reduce the clearance. But we would only do it if the experimental observation justifies it. So, quick answer, but basically there is an order you can go through, and I think this is the best way is to do this. Systematically go through this process. It's not going to get you to the final model. You're probably going to have to make some adjustments, but at least it will get you a good amount of the way, and everybody else knows that that's how you did it. So and that's really important, and it needs to be settled on, of course, not just by me, but by the field. So second thing, other data. Urine accumulation is really good data. But I think it's a question of looking for data. In fact, I'll give you one quick example of the ciprofloxacin. Liver accumulation is clearly important for ciprofloxacin. There are data out there that actually show in microsomes that if you pre-incubate ciprofloxacin with microsomes for 30 minutes, you actually get more inhibition of I think they're using phenacetin, which is a CYP1A2 substrate, and so there is evidence there, numerical data that you can fit your model to. So sometimes the urine accumulation is a great example, but often you just have to read deeper into the literature, and you can find evidence for other phenomena that people perhaps reported without really thinking it was particularly important, but actually it turns out it may be. Animal models, yes, I think the value of PBPK modeling is certainly that you can move from an animal model to a human model, and that of course is difficult, and certainly you have to be careful. For example, the enzyme kinetics may change substantially in the animal to the human, so that kind of transition is not so easy. But in the end, it's just physiology, and the drug is still the same drug. And so, the quick answer, I'm not sure I'm really answering the question here, but the quick answer is you can do it. I have not really explored that area, but I think this is, again, another issue of parameters, and how well do how well can you believe the shift in a model from an animal to a human, and what sort of parameters should you be careful with. I can't speak to that issue with any experience.
Thank you very much, Prof. Ian. I know there are a lot more questions. Again, the link to this video, the webinar video, will be shared on the Pharmacometrics Africa website. In case of any open questions, please, you can reach out to Prof. Haworth. Thank you very much for this enlightening presentation, and I can only wish you a very good day on your side.
Thank you.
Thank
Thank
you.
you, Francis.
Bye-bye.
Thank you, everybody. Yeah. Bye-bye.